Everybody, today we're going to talk about stoichiometry, which sounds like a fancy term, there's so many fancy terms in science. What it really means, stoichiometry, is mole relationships in chemical reactions. So we know that moles have to be in certain ratios to make formulas. We know formulas are balanced in a chemical reaction. So how do we solve problems? Like if I need to produce this much of a product, how much reactant do I need? And back and forth. So let's talk about stoichiometry right now. Come on, I'll take you with me. Okay, now it's getting creepy. Let's just go to the kitchen table. Yo everybody, yo, Mike here, and we're about to get back on this little problem I left hanging. Remember where we were talking about the ratios of which reactant runs out first? Is it iron or sulfur? Well, I left it hanging because I knew we'd pick it up now, because we've talked a lot about mole ratios and we're going to do a little bit more of it today. And now you folks are old enough to know that after talking about mole ratios being in formulas and balancing chemical reactions, that we can't get anywhere with this problem until we find out how many moles of each we have. And so we have to get our, remember this thing? Remember that thing? Yeah. We had a little break from it. And so what I'm going to do to figure out how much, let's say the goal was to find out how many grams of this are we going to make. And now we established when we talked about the mole as an introduction that we ain't going to make 20 grams of that. They aren't going to run out at the same time. And that's because a mole of iron weighs different than a mole of sulfur. So your first step, step one, is always to take whatever they gave you and convert it to moles, unless they're nice enough to have already given it to you in moles. So to solve this problem, I'm going to go take my friend the periodic table and I'm going to go convert from grams of iron into moles. And the periodic table tells us that in 1 mole of iron, there is 55.85 grams of iron. Grams cancel, and we get moles. So 10 divided by 55.85. Whoops. 10 divided by 55.85 is going to be 0.179 moles of iron. This is before the reaction occurs. And now the same process, except with different numbers of sulfur. 32.07 grams of sulfur is 1 mole of sulfur. And let's crank out what that's going to be. 10 divided by 32.07 is 0.312 moles of sulfur. And so if you see that the reaction dictates that they're going to react in a 1-to-1 ratio, this is the same problem you have if you're having a cookout and you want to find out, hey, who's gonna run out first? You know, are we gonna run out of buns first? Or are we gonna run out of hot dogs first? And this would be like where maybe iron is the hot dogs and the sulfur is the buns. But the bottom line is this reaction is going to come to a screeching halt. After the reaction occurs, it's going to consume 1 mole of iron, 1 mole of sulfur. It's going to make 1 mole of iron 2 sulfide. And so as the reaction occurs, the 0.179 moles of iron will disappear and become 0.0 moles of iron. And with it, it will take, as you go, you know, minus x plus x, whatever x number of moles is. With it, it will take along 0.179 moles of sulfur. And so what will happen is this will run out to go to 0, and we have a name for that I'll get to in just a second. But if we were interested in finding out how much sulfur was left over, it would be 0.133 moles of sulfur. And then as you see, what would happen here is you would start with 0.0 grams of iron 2 sulfide, but because you would make 1 mole of iron 2 sulfide for every 1 mole of iron that is disappearing, as well as 1 mole of sulfur that disappears as the reaction proceeds, this would be a gain of 0.179 moles of iron 2 sulfide. So 0 plus 0.179, that's how many moles of everything you'd make. And what would be left over. And so if we cared to find out how many grams, because that was our goal, we would need to find out what 1 mole of iron sulfide weighs. And it would be, of course, what 1 iron is 55.85 grams plus a sulfur. It would be 87.92. And we can answer our question now. Now that we have it in the context of moles, we can answer that question that we would get 15.7. Make sure I did that right. Yeah, so times 0.179 and 15.7 grams of iron 2 sulfide. So see, we didn't make 20 grams because we couldn't, because the iron ran out first, and we have names for that. And this will come back up, not in the next example, but it'll come back up again. The one that runs out, we call the limiting reactant. The one that is left over is called the excess reactant. And actually, folks, we could even find out how much was left over. Now, there's a little thing called the law of conservation of mass that says if you take 20 grams of stuff, you're still going to get 20 grams of stuff. So how come we only got 15.7 grams of stuff? Well, that's because the excess reactant is just sitting there like leftover hot dog buns with nothing to pair with. And it's just going to sit there until more iron comes along. And so you could figure that out real quick. 20.0 grams of stuff is what we started with on the reactant side, minus the 15.7 grams of product is going to say that we will have 14.3 grams of sulfur left over, or if you want to sound fancier, in excess. So you see what the first step is, and we would not have had an easy time solving this had we not gotten into the language of moles. And now this was a relatively easy example. Why is that? Because this was a 1-to-1-to-1 reaction with coefficients of 1. Really easy to kind of see where we're going with this, like where the product is. We didn't have to do any sort of ratios of coefficients, and so that's why we should do a little harder one next, and then another one after that. So buckle up. We're going to practice a lot of mole reaction ratios today. All right, and we're back. It's story problem time. And here is something that might be of, geez, I hope not, but I mean, I hope it's of relevance to you in the fact that you have an airbag in your vehicle. And by the way, I use quotes there, airbag. I'm trying to start a movement. There is no air that inflates your airbag. It is nitrogen. So an airbag is actually a nitrogen bag, and if you ever watch some videos I've done with the automotive department, I've been very vocal about this, but you know, still the world has not yet embraced my movement to call an airbag a nitrogen bag, because what happens in an airbag, wherever it's located, is if you collide with something at not right, but at a certain threshold of speed, all the voltage from your battery will be shunted into this compartment that has sodium azide. Now, you probably are bothered by that, NaN3, that's not the ratio. This is a polyatomic ion called the azide ion, and as you might have figured, it's not very stable. And so what happens is, if you give this a little zap of electricity, you'll make some sodium, which isn't very safe, but it stays in the same compartment. And then gas, which takes up 1,000 times more space than a solid or liquid, will be sort of produced very quickly and used to inflate a nitrogen bag. So some engineer here, actually in town, I don't want to brag, but good old Dayton, Ohio, this is where this was developed, I'm pretty sure, had to figure out how much sodium azide do we need in order to make a certain amount of nitrogen. It would depend on the size of the airbag. So what I'm going to do next is I'm going to make what we call a concept map. So here we got 2 NaN3 and then 2 Na and then plus 3 N2. And a lot of these problems, what you're doing is you're almost always starting with what they gave you. So they gave us the grams of N2 and they want the grams of NaN3. So there's the end of the problem, and there's the beginning, and then here's how chemical reactions work. There ain't no direct route. And yeah, I saw one book, and it's kind of humorous, but still, you have to go through Moleville, folks. You're going to have to go from grams of N2 to moles of N2. And then from moles of N2 to moles of sodium azide. And then from moles of sodium azide to grams of sodium azide. And so what we've got going on here is we're actually kind of going backwards. We're saying we need to produce this much, that's the product, and how much reactant is going to be required. So, and there's 3 steps to this process. If you go and you look up the molar mass, or you calculate it, of N2, that'll get you to moles. Here we're going to use the ratio in the balanced reaction to convert moles of N2 to moles of azide, and then we're going to use the grams per mole again, but this time of NaN3. So what we will need to do is figure out what each of these compounds weighs, and we'll do that along the way as we go and solve this problem. So once again, the only real easy thing going on, there's 2 easy things going on. We don't have a limiting reactant because there's only one reactant. So the one reactant's going to be the limiting reactant. We also only have one number, and that means that's where you should start. And almost always the place you start is convert it to moles. So to do that first step, what we're going to do here is we're just going to start with our number that they gave us, 100 grams N2. What am I going to do with that? It's almost always to go from grams of N2 to moles of N2. And if you look at an N2, that's 14.01 grams per mole. But don't forget, it's N2, and so that's 28.02 grams equals 1 mole. And you could do that off on the side somewhere. So 20, and once again, 1 goes next to moles, 28.02. And after this particular step, I am now in units of moles of N2. And that's not what they asked for. They want grams of NaN3. And so I'm going to go ahead and do that. And so we'll go ahead here. And now the next step, though, 1 mole N2. I can't convert anything, moles N2, I could convert to grams, but that's where we came from. I can convert that into moles of NaN3. And you will notice I accidentally goofed. What we're going to do next is we're going to take the coefficients next to each mole, and don't think too hard, folks, but what we're going to do is we're going to take the coefficient next to N2, we're going to put it right there. That's a 3. 3 moles of N2 must have come from 2 moles of NaN3. And so what happened is this first step came from the periodic table, but this came from the reaction. And all I'm doing is taking the coefficient next to each thing and putting it next. So yes, I multiplied by 2/3, but I didn't have to think about it too much. And sometimes thinking about things, especially with 2/3 or 3/2, that's a bummer. That's one of the reasons I also think that folks should try to balance these in whole numbers and not leave any fractions up here, because this step, there's going to be a step here in stoichiometry right in the middle where you're going to have to convert moles to other moles. And now I have moles of NaN3. Only thing left is I have to find out what a mole of NaN3 weighs. And so let's go figure that out. You got 1 Na and 3 nitrogens. And so an Na is 22.99. Well, hey, don't get me wrong. It's right there, right? 22.99 for sodium. 3 N's would be 3 times 14.01. All this in grams per mole. And so 14.01 times 3 plus 22.99 is 65.02. So you go off, and that's how many grams NaN3 equals 1 mole. So that's going to go right there, 65.02 grams. Now, you can check yourself before you wreck yourself, and you could say, did all my units cancel except what they asked me? Grams, we already figured out, cancel. Moles of N2, now it's not just moles, it's moles of what? Moles of N2, cancel. Moles of N2. Moles of NaN3, cancel. Moles of NaN3. And now the only surviving units of this process is the grams of NaN3, just like they asked. And so all I do now, multiply out the top, divide by the bottom, and so it would be 100 times 2 times 65.02, and then divided by 28.02, and then divided by 3. And of course divided by 1, but that doesn't really matter. And then we can look at that, and we could say, does that make sense? Well, it don't not make sense. I'll tell you why. 154.699 grams of NaN3. Oops. Let's be consistent. They gave us a number in 3 digits. 155 grams. Now think about this, folks. If somebody miscalculated this, you're going to under or over inflate an air bag, nitrogen bag, and that'd be bad news bears. Does this number make sense? I'll tell you what, it makes sense to me. I started with 155 grams of stuff. I need to end up with 155 grams of stuff. And as was given in the text of the problem, it's 100 grams of N2. How come we didn't get 155 grams like we started with? You probably answered that in your head already. That's because 55 grams was sodium. So it's still, now if I got a number less than 155, now why would I do that? Maybe if I were to miscalculate something here, if I were to forget this step, I know that would actually make it bigger. But, you know, if I were to get a number less than 100, I could say that's complete perversion, because I can't take less than 100 grams and make 100 grams out of it. And then there's the sodium that's not accounted for. So this number makes good sense to me. If you wanted to, you could go back and you could verify that that sodium is 55 grams. The only thing different is you would have you'd have a, instead of a 3 there, you'd have a 2 sodiums, and then you'd have a 3 there and you have 2 sodiums, and you could find out how much sodium would be produced along with it, and except this would be a 22.99 or whatnot. So you can go calculate all those 3 numbers if you wanted to. And so there you go, folks. This is mole relationships in chemical reactions, and once again, it requires practice. And quite often, you're either going to get a case where they give you one number, and then that's because there's only one reactant, or they just want one particular product to figure out how much reactant it came from, or you get 2 numbers. And so if the 2 numbers are both reactants, then you have to figure out which one's going to run out first. And we're going to do some more of that next. All right, folks, tough one coming up. I know we're into overtime here, but this is going to be a little bit harder one. And you can kind of tell that they've given us 2 numbers, and that is, here's the reaction. They were nice enough to balance it, just like the last one was balanced. If 25 grams of N2 is reacted with 5 grams of H2, how many grams of NH3? Got to keep your eye on the prize. That's what they want. Will be produced. And so we got a whole bunch of coefficients going on there, and what I'm going to do first is I'm going to go ahead and do the first step that is always, even if you don't know how to get started, it's always the same first step, or almost always the same step, unless they were pleasant enough to give you moles right off the bat. And so the bottom line is I need to convert grams to moles. N2 is part of our last problem. 28.02 grams of N2 is a mole of N2. H2 at 1.01 apiece in the periodic table of the elements, 1.01. 2 of them, 2.02 grams of H2 is 1 mole. So let's first convert those 2 numbers to moles. 25 divided by 28.02 is going to be 0.8922 moles of N2. 5 divided by 2.02 is 2.475 moles of H2. Okay. If you think of it very superficially, which would not be the right thing to do at this point, you'd say, hey, there's more moles of H2. So that's going to be the excess reactant, and N2 is going to be the limiting reactant, and that would not be the right thing to do in this case, and here's why. You would be ignoring the fact that this particular reaction requires more, 3 times as many moles of N2, H2 as N2. And so the best, okay, now this is where there's 2 ways you can look at this. There's 3 ways you can look at this. You can reason your way through it, and that means that you need experience solving these problems, and then you get more familiar with it. What you could do is you could say, I'm going to take bigger number divided by smaller number. and see what kind of ratio I get. So I'm going to take 2, and it's going to be either greater than 3 to 1 or less than 3 to 1, and that means something. So 2.475 divided by 0.8922. And what do we get? I get 2.77. So what's going on there? This is really present in a 2.77 to 1 ratio in the amounts given in the problem. That ain't 3 to 1. And so what's going on is that this is light in terms of H2. There's not enough H2 compared to N2. And if I'd have concluded, oh, there's more moles of H2, well, I forgot the 3 to 1 ratio, see? If you're a rule follower, there's always this one simple thing you can do. You can divide by the coefficient by its coefficient and compare numbers. So if I divide 0.8922 divided by 1, because that's the coefficient in the balanced reaction, I get 0.8922. If I divide this by 3, let's see what I get. 2.475 divided by 3, I get 0.825. The smaller number is going to be the limiting reactant. Why do we care about that? Because we can't go anywhere until we know which one runs out first. And just like making hot dogs and buns, if you run out of one, that's going to limit how much stuff you can make. And so what you do is you always start, either way you look at it, hydrogen, H2, is the limiting reactant. So you're going to base your calculation on this. And now it just becomes, and you ignore the other one. Now it just becomes a regular old moles to moles problem. And hey, look, I did all the work of getting it into moles. I ain't starting back at 5 grams. But either way you look at it, you could divide this number of moles by that, and it's 2.77, which is less than 3. And so that indicates that H2 is the limiting reactant. Or you could just divide each by the coefficient. Either way, hydrogen's going to run out to 0, and that's the basis of your calculation, because that reaction will stall and halt when that happens. So now what you do is you go and you start back at just like a mole to mole. Actually, we got the first step of this thing is done for us. We already got it in moles of H2. Now I can convert moles of H2 to moles of NH3. Remember, eye on the prize, that's what they wanted. And so I could say, okay, here, don't think too hard. Take the coefficient that is next to the H2, which is a 3. Put it next to the H2. Take the coefficient that's next to the ammonia, which is a 2. Put it next to NH3. And now it's just a convert moles of NH3 to grams of NH3. And a mole of NH3 is going to be a nitrogen, which is 14.01 in your periodic table, right? And then plus 3 hydrogens, so plus 3.03, because they're 1.01 apiece, 17.04 grams of NH3. Now, before I finish, and before I do this, this number that I get sure as hell better be less than 30 grams. Because I only have 30 grams of stuff. I can't make anything more than 30 grams of stuff. And so let's see what we get. 2.475 times 2 times 17.04 divided by 3. 28.116. Everything was to 2. 28.116 grams of NH3. That is less than 30. Let's make it consistent. Those were good to 100th. 28.12. grams of NH3. Makes sense to me. Like, we started with 30 grams, where'd the extra 1.88 grams go? That was the limiting reactant, right? Or the excess reactant. It's going to sit there and do nothing, just like hot dog buns that don't have any more hot dogs. You have to feed them to the squirrels. Except don't feed nitrogen to squirrels. That's you know, not in pure form. They would that would be not nice. So, folks, you stuck in there overtime today. Thank you for doing that. Next one will be a little shorter, but we're going to do some more stoichiometry problems, except this time not with grams, but with solutions and their concentration. So we'll see you next time. Take care.